2, 1, another 2070 video, and so today we're going to be talking about diagonalization, one of my favorite phrases here in mathematics, and broadly speaking, it's going to be a process of transforming a matrix into a diagonal one. So let's start off by defining what a diagonal matrix is, and it's a great case of the name tells you exactly what it is. It's a matrix that looks like a diagonal. For example, right, so precisely, right, what's going on is that the entries that are not on the diagonal have to equal 0. So if you're looking at the j-kth entry, so the entry in the jth row and the kth column, if the row and the column are different, so for example, up here I'm in row 3, column 1, you gotta have a big fat 0 there in order to be diagonal. Right. So note here that I do have a 0 hanging out on my diagonal, so that's the 3, 3 entry, and that's fine. You can have 0 entries on your diagonal, that is allowed. Now note something about diagonal matrices. They are clearly triangular, right? Note this matrix is both upper and lower triangular. It's upper because the entries down here are equal to 0, and it's lower because the entries up here are equal to 0. So it's a triangular matrix, and thus the eigenvalues are simply the entries that are on its diagonal. So that's quite nice. So diagonal matrices, similar to triangular ones, are very good because I can immediately read off to you the eigenvalues. So this matrix D has eigenvalues -1, 2, and 0. Right, that is the last entry down here. All right. Now, since the entries on the diagonal of the diagonal matrix are the only ones that could possibly be non-zero, they usually get special designation and given a diagonal matrix D, the kth entry, so the entry in the kth row and kth column, we'll typically write that as D sub k, rather than D sub kk, because, yeah, right, you know what's going on. See, it's the entry on the diagonal we care about. Alright, now, last time we finished things up by talking about similar matrices, and so diagonalization is saying that we are diagonalizable, so precisely if you are similar to a diagonal matrix. So again, recall being similar means that I can get from one matrix to another by multiplying by invertible matrices on the left and the right. In particular, we multiply on the left by P inverse and on the right by P. So you're diagonalizable if I can find some matrix P so that P inverse AP has to equal D, our diagonal matrix. Now recall, the reason we pointed out similar matrices and noted that these were seemingly an important thing is that similar matrices have the same characteristic equation and thus must have the same eigenvalues. So if A is diagonalizable, then the diagonal entries D1 to Dn on our matrix D have to be the eigenvalues of A, right? They're the eigenvalues of D, and A and D have to have the same eigenvalues. Furthermore, this equation right here, I can multiply P on the left, and I get PD has to equal AP. Recall that the columns of A times P have to be the columns of P times A, so we see that on the right. Similarly, the columns of P times D have to be the columns of D times P. But note for a diagonal matrix, its columns are just the scalar multiples of the standard basis elements, and multiplying a matrix by the standard basis elements will just get you the columns of the matrix on the left. So the columns of P times D are just the columns of P scaled by those eigenvalues. So note, we have to have APK is equal to DKPK, meaning that the columns of P have to be the eigenvectors associated with the eigenvalue D sub k. And furthermore, since P is invertible, we know that then all of those eigenvectors must be linearly independent. Ooh, good stuff. So here we see that diagonalization can only happen if the matrix D that you're diagonalizable to is the matrix consisting of the eigenvalues on the diagonal, and the matrix P consists of the associated eigenvectors placed accordingly. Exactly what I just said. All right. So the only way you can be diagonalizable, the only way you can be similar to a diagonal matrix, is if you have enough linearly independent eigenvectors. Then the matrix P can be formed by just putting in all the eigenvectors, and necessarily this product has to then be a diagonal matrix with the eigenvalues on the diagonal. Right? Just by the derivation we did before, A times P and P times the matrix D, either they have to line up with each other. All right, so the process of diagonalizing a matrix then boils down to get eigenvalues and get eigenvectors and put it all together. All right, so for this matrix right here, -2, 4, 1, 1, let's get the eigenvalues, get the characteristic equation. Eigenvalues are then easily seen to be -3 and 2. All right, and then for each one of these, we will produce eigenvectors. So the eigenvectors for -3, add 3 on the diagonal, you get this. From there, we see that v1 plus 4v2 is equal to 0, so v1 has to be -4v2, and there we go, a basis for the eigenspace associated to this eigenvalue is -4, 1. And then a similar derivation can be done for the eigenvalue lambda equals 2. Basis for the eigenspace is the vector 1, 1. So then the matrix A can be diagonalized, and that means I can multiply A on the right by P and on the left by P inverse and get the matrix D. The matrix D has to be the eigenvalues, so -3 and 2, and the columns of P have to be associated eigenvectors. So note the entry here, -3, the first column has to be the eigenvector associated with that. And again, we found a basis for it, and so that's one we picked. You can pick any scalar multiple of this, doesn't matter, but obviously we picked the cleanest one we can find, which is this. And similarly for the eigenvalue 2, the vector 1, 1, as we saw, is a basis for its eigenspace, so that's one we pick. Now, it's worth noting that if you want to do the full-on diagonalization, you would also compute P inverse, and that's this matrix right here. All right. Hey, beautiful. So we've taken a matrix and we've demonstrated that it's similar to a diagonal one, and we found that the diagonal matrix it's similar to has to consist of the eigenvalues, and the matrix that gets us there, the similarity transform, multiplying by P inverse on the left and P on the right, has to consist of the eigenvectors as the columns, and we did it. All right, so that was beautiful and everything worked out perfectly. But in mathematics, whenever you do cook up a definition, you want to do two things. You want to show something that works and something that doesn't, right? Because if everything works, then that's not a definition, and if nothing works, then it's also not a good definition. So it's possible that not every matrix is diagonalizable. And what's mildly frustrating in the name is that diagonalizable means that you're similar to a diagonal matrix. It doesn't mean that you kind of look like a diagonal matrix, because, for example, if I didn't tell you what diagonalization is, if I just said, hey, we're going to talk about diagonalization today, the process of diagonalizing a matrix, I didn't give you any formal definitions about that. I didn't say that, oh, I mean specifically the similarity maneuver. And if I just said, hey, we're going to diagonalize matrices, and I gave you this one and I asked, can you diagonalize this? You would look at that and go, well, yeah, it's almost diagonal. The only issue is this one up here. But diagonalizable matrices are the ones where we have enough eigenvectors, right? Because a diagonalization for us is the similarity transform. It's not just sort of a visual, does this look diagonal? Is this close to being diagonal? And this matrix fails to be diagonalizable because, note, it's upper triangular. So its eigenvalues are precisely the entries on its diagonal, but we only have one showing up to the party. And for this eigenvalue 1, subtract 1 off the diagonal, then we see that the only eigenvector equation I get is that v2 is 0. So 1, 0 is a basis for the eigenspace. I only have one linearly independent eigenvector I could possibly find, right? Obviously, 1, 0 is our preferred choice, but we can find other ones. Any non-zero multiple will work. But in order to be diagonalizable, this is a 2 by 2. I need two linearly independent eigenvectors independent. What is this word? This spelling is like atrocious. Right. So I can only find one, but I need two to be diagonalizable. So this matrix fails to be diagonalizable. Oh man, that's pretty bad. All right. So unfortunately, there are matrices that just can't be diagonalized, and well, maybe you might think that's not a bad thing. Like, right? Why are you bothering these matrices, making them be diagonalizable? All right. Now, note something about this matrix. This matrix had an interesting feature in that the eigenvalue only had one, right? And that's because its characteristic polynomial is lambda minus 1 quantity squared. So, for the deep lore enthusiast, if you want to follow this idea a little further, this matrix has only one eigenvalue, and its eigenvalue has algebraic multiplicity 2. And the eigenspace is only one-dimensional, so the geometric multiplicity of the eigenvalue, lambda equals 1, is 1, since there was only a one linearly independent eigenvector that we could find. Ooh. Turns out the geometric is always less than or equal to the algebraic, and that's a fun little thing. So for the interested individuals, you can explore that a little further. But let's wrap up things today by noting that if you do have an n by n matrix, and you are not in the situation we were just in, where we had a repeated eigenvalues, so let's say I have an n by n matrix and I have n distinct eigenvalues, then it is going to have to be diagonalizable because any list of associated non-zero eigenvectors are going to be linearly independent. So if you have a matrix that has, like, let's say it's a 3 by 3, and you've got 1, 2, and 3 as your eigenvalues, then it has to be diagonalizable. So not all hope is lost. As long as you sort of have a unique set of eigenvalues, then you must be diagonalizable. And this is a fun little argument. So let's wrap up things today by proving this, that if you have distinct eigenvalues, then the associated eigenvectors have to be linearly independent. Okay. All right. So suppose that wasn't true. Well, v1 is a non-zero vector, so it's got to be linearly independent. Right, we know that. And since the full list fails to be linearly independent, that means as we go down the list, at some point we are still linearly independent, but the next vector has to be a linear combo of the previous ones. Right, so at some point we fail to be dependent. We fail to be independent, which means whatever vector I got added has to be a linear combo of the others. Now let's do two things to this equation that I have right here. Let's scale it by the next eigenvalue, dp1, and let's multiply by the matrix A. Note when I multiply this by the matrix A, on the right I'll get dp plus 1 vp plus 1 because this is an eigenvector for A with respect to the eigenvalue d sub p plus 1. And multiplying all of these will just give me the associated eigenvalues. Right. Now, I can take the difference of these two equations, and that gives me this. So note on the right-hand side, we got a big fat 0. And hopefully you see where this is going, because now, hey, I have a linear combo that is trivial, and my vectors then, since they are linearly independent, forces all of the scalars to equal 0. All right, but that's going to mean that these things right here are all non-zero, right? All of these are non-zero because the eigenvalues I have are different from each other. So when I get to the p plus 1, it's different than all of the prior ones. So the only way I have zeros for all of these numbers here is if the scalars c1 to cp is 0. But if that's true, then going back to this linear combo, I get 0. But that runs contrary to what we've assumed, that the vectors I'm dealing with are non-zero. So, contradiction. So it's got to be that the full list is linearly independent. At no point does the list start failing to be linearly independent. Beautiful. Slick little argument. I like that one. All right. And with that, we are wrapping up, for now, the conversation on diagonalization. We'll return to it towards the end of the semester.